Very good. Welcome back. In this second part of the class, we're going to be talking about how we design a theory of probability as a tool that's supposed to help us achieve a certain function, uh, fulfill a certain purpose. So what I'm going to do now is switch over to my tablet, and so the idea here is we want to talk about what's normally, we have to introduce a few names every now and then so that you know how people talk about these things. Inductive inference or inductive logic is the term that is many times used when reasoning with incomplete information. The idea is that if you have complete information in a certain problem, what your inferences are going to be called deductions. When the information is not complete, then you talk about an inductive inference, an induction, or and in the case of complete information, the rules are going to be the rules of logic. And in the case of incomplete information, people used to say, at least, the rules are those of inductive logic. Well, now we just say it's the rules of probability theory. So our goal is going to be to obtain those rules. For that, we need to be very clear about what it is that we're trying to achieve and how we're going to do it. Let me start by reminding you that we all know what the rules of probability are. We have a sum rule and we have a product rule. The sum rule applies when you have the probability of two sentences, two propositions that you want to ascertain whether they're true or not, and you say the probability of A or B, this symbol here means it's a wedge. This means or. The probability of A or B is going to be given by the probability of A plus the probability of B minus the probability of A and B. And here, when we just have like a product there, this is going to be and. Similarly, the probability of A and B is going to be the probability of one of them multiplied by the probability of the other given the one. Now, I'm sure you've seen this before, and I'm also sure that some of you may not even remember precisely what this is, what it comes about, what it all means. This is the purpose of this class, to make sure that by the end of the next couple of weeks, you can dream about these things and know exactly what's being said. The point I want to make, however, right now is that we have the formulas. So what's the big deal? The big deal is the following. What does P mean? What is a probability? That's the main issue here. While we know precisely what the formulas that work well in the world are, the fact that there are many opinions about what probabilities mean is a serious impediment to progress. And I'll give a couple of examples in a second. Something analogous to this. So here we know the mathematics, and we have a problem with the interpretation. Similarly, we know exactly what the laws of quantum mechanics are. We know exactly what they are. We know exactly how to compute with them. However, we have an interesting problem here in that we do not know what the wave function means. So what is the interpretation of psi? That is a serious problem that is precisely analogous to that one. What do I mean by what is the interpretation of psi? We all know that if we take the magnitude square of psi, that gives us a probability. In fact, it gives a probability density, right? So we can actually be a little bit more precise about this. The probability of detection of X. Very nice, but when we say this is the probability of X, what do we mean by that? Do we mean it is the probability that if you place a detector, you have a beam and you place a detector at the location X, that detector will click or not? The probability of a successful outcome? Or is it the probability that the electron was there originally and that's why you detected it? Is this the probability of detecting, finding the electron? Or is it the probability that the electron was already there? This kind of distinction drives people who study quantum mechanics in completely different directions. If you believe that the electron was not there, that it makes no sense to talk about the electron having a definite position, and what has a definite position is the detector that finally goes click when it gets hit by something that wasn't there. That's the Copenhagen interpretation. It's an interpretation that's been very, very successful throughout all of the 20th century and well into the 21st. And if you don't use it properly, you don't pass your comprehensive exams. So it's actually important to know how this works, right? So that's one interpretation. The probability, the X refers to not the electron, refers to the detector. Then there is another type of probability that says, no, X is the probability of the position of the electron. The Bohmian interpretation, the de Broglie interpretations are very much along these lines. The electrons have definite positions. When they go through a double slit, in a double slit experiment, the electron goes through either one slit or the other, not both, or neither. There is a trajectory that the electron follows, and then, of course, you compute the probability using these funny formulas. That's a very interesting interpretation, one that I find particularly appealing. But let us be very clear, it's completely different from Copenhagen. So which one is it? Yet another interpretation is that, no, you don't really talk about probabilities in quantum mechanics. The wave function describes everything, and when the wave function says that you could be in either this state or that state, it's because there are two different universes. In this universe, the electron is doing one thing. In this other universe, it's doing something else, and these universes are bifurcating completely and constantly all the time. Now, that's a very, very different picture of reality in which you have many universes as opposed to one. So the point of all of this digression is to point out to you that even when you have a well-defined mathematics, the issue of interpretation is crucially important, and it's exactly the kind of thing that can derail a research program completely, and you can spend decades of your life just studying the wrong types of solutions, and they don't work, and you do not know why. And so what we're going to do is the following. The usual approach is you have a mathematical framework, a formalism, and you add an interpretation, and this is what gives you your theory. So for example, the formalism could be the Schrödinger equation. Then you try to append, and I like the word append because it gives you the impression that you have this mathematical structure, and then you come and you stick something foreign to it, a meaning, an interpretation, and then you have a full theory. But as we see in the case of quantum mechanics, you can add different interpretations, and the fact that it is not obvious which is the correct one can be a real problem, because you do not know how to quantize gravity, you do not know how to do quantum cosmology, you do not know if there are many universes or just one, you do not know whether the electron has a position or not, which obviously is important to do gravity. Position matters in gravity, it's very geometrical. So what we're going to be doing, so here's the problem. It's not obvious how to invent interpretations. So what we're going to be doing is doing it exactly opposite. We start with a very clear sense of purpose. Let me see, what is it we want to do here? Well, start with an interpretation. We start with a very clear idea of the subject matter. We're not talking about detectors, we're talking about particles. And to this, we do not append anything, we just proceed to design tools. We design a framework so as to be able to derive the mathematics. So we derive the mathematical framework. And this is what our theory is going to be. But it's clear that we start with what we want to do, and then we proceed to try to do it. We design the tools to be able to accomplish that. And so it is this final set of ideas that produces what our theory is. Now, why is this better than the previous one? Well, the reason this is much better is that the interpretations are things we talk about. They're fluffy. They're coming in languages, in human languages. And therefore, they're very difficult to compare with experiment. On the other hand, here we start with a more or less clear language. We proceed to design the mathematical framework, and the mathematical framework is what we can compare to experiment. So here we would be trying to compare to experiment things that always produce the same numbers, because it's the same mathematical formalism. But in this second version, we're trying to compare to experiment different mathematical frameworks, and we would be led to different mathematical predictions, and therefore some might agree with experiment or not. So the crucial thing we might want to claim here is that this is what can be compared to experiment. Comparing this to experiment That's what can be done, but it tells you nothing about this second part. While here, we start with that, and if it leads to the correct mathematical framework, because it agrees with the experiment, we know we're in the right path. For example, you may start, I'm going to build a theory about particles, and the particles are going to move in certain ways. And I'm going to put all of that information and come up with a mathematical framework. Well, if the mathematical framework does not satisfy a principle of superposition, then you immediately say, yes, there is something wrong. On the other hand, if you start with the principle of superposition, you have no idea of what to do here. You see where this is going? And this is what we are going to be doing. Very good. We're going to start by doing that for probability theory. Of course, the way people dealt with probability theory throughout history has been starting in this first approach, while we are going to do it in the second approach. So let me say that in different words. In the approach A, this is what we are not going to do. Let me write it like this. We are not going to show that probabilities are Bayesian degrees of belief. These are terms that we're going to explain in full and glorious detail as we proceed. What we are going to show is that Bayesian degrees of belief follow the rules of probability. Now, this at this point, this is sort of course, vague, because I'm just trying to fly over the territory from a distance so that you can see where we're going. But please notice the huge differences between this approach, in which we know what the rules of probability are, but we have no idea what that might possibly be, as opposed to saying, well, if we want to build a theory for these Bayesian degrees of belief, then we derive the rules of probability. In this circumstance, the problem of interpretation is completely settled. Towards the end of the semester, we're going to do exactly the same thing with quantum mechanics. First, we're going to do it for just probabilities, then for probabilities as applied to statistical mechanics, introducing notions of entropy along these lines. And then we're going to push this and push it and push it further until we get all the way to quantum mechanics. Very good. So now I said here that if you start with the rules of probability, you append an interpretation, eventually you end up getting theories and you proceed. But what are those interpretations? So let us go over quickly what is the menu you have to choose from. There are many. Okay. One of them, the most popular one, and it's probably what you have learned, is the frequentist. The frequentist interpretation of probabilities, frequentism. The idea here is if you have a phenomenon that can be repeated a large number of times, you have many trials, you just count the number of outcomes of a particular type, and so the probability of that outcome is going to be the ratio of the number of successes over the whole number of trials. This is a wonderful way to think about probability. And you see how I'm picking my words carefully here. It's a wonderful way of working with probability. It's so wonderful that it has formed the foundation of the whole of science in the 19th and 20th century. So this is really good. Unfortunately, you run into troubles when you have when you want to think about some problems. So for example, if you need to have many trials, toss the coin 1 billion times and then figure out the number of heads, and so you take the ratio that gives you the probability of heads. If you're going to have to toss the coin 1 billion times, one of the advantages is at least you have this illusion that you're doing something very objective, right? You can do the experiment. Well, it's not quite so, because nobody goes there and tosses a coin 1 billion times. The probability thing as a frequency would require an infinite number of times, which are not experiments you can actually do. But you have problems with this. One problem, which is very serious, is the following. Suppose that I have my coin, here's my coin, and I toss it. You might complain, wait a minute, you didn't toss it, you placed it. If you always place it in the same way, it's always going to be heads. There's something funny going on here. Yeah, you're supposed to toss the coin and in such a way that it is a random process. What does random mean? Are you saying that the laws of physics do not apply, the laws of classical mechanics do not apply to the tossing of coins? You tell me precisely what is the initial condition, and you tell me precisely what is the friction of the air, and you tell me precisely how bouncy is my hand. And if you tell me precisely what's going on, I compute it. It's not random at all. So where do probabilities come in here? The term random is not so easy to define properly. Another problem with this is how large the number of trials. Here's another problem. What happens when you have no available ensemble of trials? For example, if I were to ask the question, what is the probability that there is life on Mars? It makes sense to say, well, let's say 30%. It appears to make sense, right? But on this interpretation of probabilities, it makes absolutely no sense, because are you going to conceive that there are copies of the solar system with different planet Mars, and somebody is in principle, or even ideally, capable of counting the ones that have life or not? So for some problems, there are no ensemble of trials. Here's another one. What's the probability that the nth digit of pi, say, count 10 to the 43 digits, what's that digit of the number pi? Is it a 7? What's the probability it's a 7? 1/10, right? And yet, are you going to imagine that there are different numbers, pi, in different universes, or whatever, different trials have different pi's, and so that in principle you could have a collection of pi's? Makes no sense. So this is actually the most serious problem when you don't have many trials. You just have one. I'm interested in whether this universe is of this type or that. I don't want to have a cosmology with many different possible universes out there. This is the universe I'm concerned with. This is the planet Mars. This is the particular digit of the number pi. And quantum mechanics is precisely like that, because quantum mechanics is not a theory just for ensembles of experiments. You want to be able to make predictions for single experiments, and you want to be able to think about single experiments. So frequentism, despite its great advantages and great intuitive appeal, has its problems. And the truth is that by the time that people end up answering these questions of what do you mean by random, how large has n to be, what happens when you don't have ensembles of trials, when people start getting even close to answering these questions, it's the intuitive appeal is completely lost, and the possibility of claiming that you can actually measure probabilities is completely lost. Well, there are other approaches to probability people realized early on. There is the propensities, a degree of propensity. When you toss a die, the die has a certain inner oomph, its propensity to land on the number 2. The person who invented this idea was the philosopher of science Karl Popper, and this is a particularly interesting approach. Nobody has ever managed to do anything useful for it in physics, but I want to point out that there is this idea of a probability is it's like a physical inner force for a particular outcome to become instantiated, to become true. Another concept of probability that's particularly interesting too is the idea of a potentiality. I do not know very well what is the difference between a propensity and a potentiality. What I can tell you is that this potentiality is something that originates with the Greeks, but the person who really tried to put some words into it and tried to envisage this as being part of physics was Heisenberg. This is what he thought of probabilities as being. There is another modern one, which is what's called like a degree of objective chance. The philosopher David Lewis was involved with that, and so people have discussed. This goes back to 30s or 40s, I think. In any case, so there are many of these alternative possible interpretations to probabilities. This one has been particularly successful, even though we understand it's limited. These other three, I do not think they have been particularly successful. One of the things that they all have in common is that they're supposed to be objective. They're supposed to represent something physical. So these ideas are trying to describe probabilities as being part of physics. You may want to figure out how an electric field moves around. You would like to figure out how these fields of probability, or whatever they are, move around. There's something, there is an inner something in these physical systems that tells them that they're supposed to behave with a certain propensity, or for a phenomenon to become potentially instantiated, or that there is an objective chance for your coin to land heads. Very interesting. If this were true, then the computation of probabilities would be a problem of computation, or the understanding of probabilities would be a physical problem. What I want to do now is discuss another set of interpretation of probabilities, the Bayesian interpretations. And did you see the plural? Bayesian interpretations. There are many. In this case, these interpretations are not objective. They are what's called subjective. And we're going to come back to these terms in a second. The idea here is that, and the first example is what is called a degree of personal belief. The degree to which a particular person, me for example, believes it's going to rain. I look out the window, I say, no, it's not going to rain. It's pretty sunny, so my probability for rain is 10%. Then clouds come around, then it's, oh no, it's getting cloudy. Maybe it's 45% now. And where does 30%, 45%, where do those come from? It's my personal introspection. It's a way of my measuring how much I have an opinion or how much I believe something is going to happen. But this is very personalistic. So this is subjective. And so one possible objection, and I think it is a serious objection, is how can you build a science like physics on the basis of somebody's personal beliefs? Wouldn't you want something a little bit more objective, a little bit more fixed? Today I'm in a good mood, so the probability is this. Tomorrow I'm going to be in a pessimistic mood. The probability is different. What makes these things work? Anyway, it's not obvious, and very smart people have actually pursued this with lots of energy. This is the kind of interpretation that is involved or is used by people who are trying to produce an interpretation of quantum mechanics that's called, originally called, or the first versions were called quantum Bayesianism. And the more modern, or rather splintered groups have gone in different directions, and this is what they call cubism. Obviously, the connection to quantum bits and things like that, and qubits and things is very clear. At the very least, these guys have an amazing ability to come up with catchy names, which is one of the reasons why people like it. But the fact that it is so personalistic, so divorced from rigid rules for computation, which is many times what we actually need to make progress in science, makes it a little bit dubious. In fact, these people have tried to derive the laws of quantum mechanics from these concepts, and so far, there is no success. So, can we make it a little bit more less subjective? Well, yes. There is what is called a degree of reasonable expectation. Sometimes they're called degrees of implication. These are different names for concepts, and you could say when you can draw a deduction, A implies B. If A is true, then B is true. Okay, A implies B. This is true. That is true. That's a deduction. But now let me say A implies B. If we know that B is true, you cannot go back. You don't have certainty that A necessarily is true. So the implication is not complete. Maybe there is a degree of implication. So this is what this approach here tends to wants to formalize, and it's very successful. Our local proponent of this kind of theory is Kevin Knuth. When you see him drawing different little lattices and thinking about doing inference, he's adopting Bayesian interpretations of probability, in which the probabilities are degrees of implication. I tend to favor the first one, degree of reasonable expectation, but the name I like better is a name that's very, very common, is a degree of rational belief. The degree to which we ought to believe in something if only we were trying to be as rational as possible. Now that's a mouthful, right? But there are certain things that we have to explain here. First, you might feel a little bit uncomfortable by the use of the term belief. Beliefs and opinions are things that are a little bit wishy-washy. Can you build science on the basis of concepts that are wishy-washy? That's an interesting one. Another source of objections to the term belief is that, at least in English, the term belief has connotations that bring it close to religion. And if there is something you don't want to do is mix your science with your religion, because they don't tend to live very well together. For some people they do, for some people they don't. But in any case, let me reassure you that when I say belief here, I do not mean to imply that there is any connection to religion. What I mean is precisely, I believe it's going to rain. It's getting cloudy. My beliefs that it's going to rain are going up. And that's pretty rational. The rational here is another term that's kind of like a tricky one, because claiming that something is rational is also not very, very clear. Philosophers have tried very hard to figure out what do you mean by rational. The way we're going to handle it is precisely the opposite direction. It may not be easy to say when it is that that argument is rational, but it is much, much easier to say when it is that an argument is irrational. Spotting irrationality is much, much easier. So what we're going to do is try to come up with our probabilities and figure out how things work by eliminating irrationality, eliminating inconsistencies. Very good. There are a couple of words here that we should address with a little bit more care. One of them is the word objective, and the other one is the word subjective. This has been, the use of these terms has been a tremendous source of confusion in the business of inference. Typically, we say that something is subjective when it refers to people's, to the individuals, to the subjects, and so the personal opinions or things like that. While objective is what's actually real. But the confusion arises because these terms can be used in two different senses, two different meanings. And one of them, we could call them ontological. Oops, watch out. This is becoming philosophical very fast. Well, these are terms that once you learn to use them are extremely useful. Ontology is the branch of philosophy that deals with existence or being. What does it mean to exist? What does it mean to be? While epistemology is the branch of philosophy that has to do with knowledge or and opinion and belief. So when we say that something is real, something is, let me give a couple of examples here. Okay, yes, before. Good. Pains and emotions are ontologically subjective. Whatever your pain is, whatever your emotions are, maybe they live in your brain or whatever, but they are yours. They depend on you, on the subject. So they see, ontologically, they are subjective. Atoms and chairs are ontologically objective. They're real, they exist. When we talk about atoms and chairs, we say they're real, right? They're physical. Yeah, that's fine, but pains are real too. We call these objects ontic. It's kind of amusing. In the Middle Ages, philosophers in the universities of southern Spain, this was in the Middle Ages, this was the civilized part of Europe, and these were Moors and Muslims and Jewish philosophers mostly, with some sprinkled with a few Christians that came to study there. In the Middle Ages, people were very, very concerned of the nature of atoms, about the nature of atoms. And so the idea, the real problem was, are atoms real or not? Do they exist or not? Today, the problem is quite the opposite. Chairs are supposedly made out of atoms, but what is a chair is an interesting philosophical concept too, because what is a chair? It's a collection of atoms designed with a certain shape that's supposed to perform a certain function. But you see that the essence of the chair then, if it is a collection of atoms with a certain shape that's supposed to perform a certain function, the essence of chairness is not in the object itself, but it is in how we humans are going to use it. So philosophically, the concept of atom is fairly clear. The concept of chair is not nearly as clear. Okay, I'll leave you with that thought for a little while. So in the Middle Ages, chairs were real and atoms were a subject of discussion. Today, it's just the other way around. Atoms are real. Real is what atoms are. That's interesting. Now, values are yes, are epistemologically subjective. Values are not real objects. They don't exist out there. They are something epistemic. Values are epistemologically subjective. Your values need not be the same as mine. They depend on the subject. While facts are epistemologically objective. It's raining. There is a truth to the matter there. So you see that whether we're talking about something being subjective or objective, we can get confused depending on where we address this issue on its ontological or its epistemological sense. So probabilities, let me write Bayesian probabilities. Bayesian probabilities are ontologically subjective. They're not like frequencies or propensities or potentialities. They're ontologically subjective. They're tools that we humans use for reasoning. On the other hand, they epistemologically, as representations of knowledge and opinion, but epistemologically they are hybrids. Sometimes your probabilities can be extremely wishy-washy, like a personal probabilistic, a Bayesian personalistic interpretation. This reflects my feeling that it may rain or not. And this is actually very important because so much of what we do as humans depends on people's opinions and beliefs that are very, very personal. So, for example, how do you even measure these things? Well, one possibility, and this is the way people who personalistic Bayesians do this, is how do you measure the degree of belief of an individual? Well, you ask them how they would bet. Would they put so much money in this or so much money in that? Which way do you bet? So depending on how much money you're willing to put, place a bet on, you can sort of have an idea of the inner Bayesian probabilities, the degrees of belief that this person assigns. On the other hand, if I give you a perfectly symmetric die, and I ask you to toss it and ask, what's the probability of getting the number 6? Of course, it has to be 1/6, right? I told you, it's perfectly symmetric. So that's a case in which the probability is epistemic, it reflects my opinion, but if I say anything else different than 1/6, I am wrong. I'm going to lose money if I bet on that. So there is one way to do it, and that makes it very objective. So that's what I mean by saying that probabilities can be hybrid. They depend on the information you have, but sometimes the information is difficult to translate into probability. But sometimes it's easy to translate into probability. In those circumstances, it's very objective. So probabilities can span the spectrum from being subjective to objective in an epistemic sense. So probabilities are epistemic objects. They're not ontic. So probabilities are epistemic. So these are the terms that are particularly useful to talk, because whether something refers to your state of knowledge or something refers to the physical reality is something that's very important in physics. If you catch my drift, you're going to start seeing here that the laws of physics contain ontic elements. They refer to things that exist out there, like atoms, chairs, the weather. But they also include concepts that are very epistemic, of very different nature. They include concepts that are used for reasoning. So that's what makes the laws of physics interesting subjects. They're not pure reality. They're reality with some additional elements that have to do with inference about reality. In particular, wave functions are epistemic. They have to do with probabilities. And objective. If you compute the wave functions wrong, you don't agree with experiments. You believe the wrong things. So wave functions are going to be epistemic and objective. Please notice how different this is from, say, the many worlds interpretation, in which the wave function is objective and ontic. It's real. It really describes how universes split. Very good. Let me see. I think that this is a good place to stop. What we're going to do next time, after setting up some notation, is going to be to get the mathematics of this rolling. After all, if we want to have a theory of probability that's pragmatically useful, we ought to be able to compute with it. That's what we're going to do next time. See you then.